All right, so today we'll be covering heat transfer, but now with fins. So you might have seen, in things like your radiator or other devices that require heat dissipation, you might see um, like protrusions that come out from the main block, and those are usually fins. And the whole point of fins is to basically increase that surface area through which uh, the heat can then be dissipated um, when we have a hot block. So to draw what a fin would look like, let's say that we have a block right here, um, and we have this protrusion coming out of it, and this would be a fin. And so if I was to, label other aspects of it, we would see that for the temperature profile, we would have something like a hot high temperature, a hot block, and that would slowly decay over the course um, of the fin. So this would be the temperature profile. Let's say um, T pro in red. And if we were to now add dimensions to this, what we can consider this is we have a specific thickness, right, over here. We'll call that 2b, right? And what that means is if I was to split this, right, make this completely symmetrical, this top half would have thickness B and this bottom half would have thickness B. Now, why are we doing that, right? What's the point behind that? Well, the point is we have convection going on below, right? We have the T bulk or T air above and below. And so in order for the problem to become as simple as possible, we can use the symmetry, but that would require us to divide this whole system in half, which allows us to put B, which is the thickness of the block, divided by 2, as the thickness that we're going to use. And then obviously there's a length and a width. So uh, this part would be L. So we have L here, and we have W, which is the width. And those are all important parameters. Okay, so now that we have a basic intuition of how a fin works, let's get into the math of it. So we have to start off with the 1D fin equation. Since we're going to only be dealing in the x direction, usually this would be a PDE, but now this becomes a total derivative, so it's an ODE. So we have this. So the second derivative of temperature with respect to position, H over BK. So B is that thickness that I was talking about. H obviously is the heat transfer coefficient, and K is the conductivity of the fin, dependent on the material. Perfect. And then another thing that we have to know is the fin parameter. The fin parameter. And what is the fin parameter? Well, the fin parameter basically just tells us how fast that heat is going to get dissipated in that fin. And so when I write out m equals square root of h over p divided by k over ac, where p is the perimeter and ac is the cross-sectional area. And so you'll see that this is basically comparing the rates of heat transfer from convection in the numerator and conduction in the bottom. And you'll also see sometimes m written as lambda, but it's not the same. So m is also m equals 1 over lambda, and lambda is considered as the penetration depth. So you might see this if you ever see m's or lambdas and you need to convert to the other, just know that it's the inverse. Okay, perfect. So now what we can do is jump into the ODEs. So the first thing that we're going to do is non-dimensionalize the ODE, just so that we don't have to deal with non-homogeneous boundary conditions. So um, you'll see that later. So first thing that we're going to do is we're going to define a new variable called theta, and we're going to set it equal to t of x minus t infinity. Oh, that x was sloppy. I'm going to go back and edit that. But we have t of x minus t infinity divided by t base. So that's going to be the temperature at the main wall. So this would be T. Perfect. So this is our theta. This is our new non-dimensional temperature. So non-dimensional. And so we also need to non-dimensionalize our position, our x. So we're going to make a new variable called psi, and we're going to set that equal to x divided by L. And so basically dx equals L d psi. So non-dimensionalized. Perfect. So now that we have the non-dimensionalized variables, we need to put them into the new ODE. And so the new ODE is going to be um, d squared theta divided by d psi squared, right? And that's equal, and that's equal to ml squared times theta. So this is our new ODE. And you can check that we can go from this 1D fin equation over to the non-dimensionalized version if you want. But the whole point is that now it doesn't look as as messy, to say that we don't have to deal with this difference in temperature or the H over BK stuff. Perfect. And so the hallmarks of solving uh, any sort of differential equation is to know first what your boundary conditions are, right? Because you want to be able to solve for those variables. So it's important to know what the boundary conditions are going into any fin problem. And I'll cover all the main boundary conditions, and then I'll be implementing one of them so you can see how that process works. But we have the boundary conditions. And so first kind that you can have is an insulated tip, right? So what that means is we have no heat going through the end of that fin. And so what that means is if I was to put it in the terms of the original variable, that means dt dx at x equals L is equal to 0. But if I was to put that in terms of our new non-dimensionalized variable, that would be d theta d psi at psi equals 1, that equals 0. All right, perfect. I'll be writing everything else in terms of theta, but if you want, you can see the basis for temperature, the original variable. The other thing that we can have is kind of the opposite of an insulated tip. We have convective tip. So we actually have convection going on. This is a little bit more realistic. You're never going to see anything that's completely perfect insulator. So a convective tip can be pretty realistic. So if I was to put this in terms of theta, it would basically be trying to say that the conduction at the end of that tip, right? So the rate of heat transfer through conduction has to be equal to the rate of convection or heat transfer that's going on at that same location. And so this is Fourier's law, Newton's law of cooling. We've combined the two to show that they're equilibrium. All right. Another one that you could have is a prescribed temperature. So we have a prescribed uh, temperature at the end of the tip. And so what that means is we basically have theta, we have theta L, and that's equal to TL minus T infinity. So that's another one that you could have. And then the final one that, is the most unrealistic, but sometimes used is an infinite fin. So assume the fin is infinitely long. And what that does is it basically forces the temperature to, at the end, to be 0. Because the fin is so long that if I was to, look back at this temperature profile, you can see that this red line would go all the way to the bottom, and there would basically be a point and where we have no more heat transfer because it's in equilibrium with the outside T bulk infinity temperature. And then one last boundary condition that all of them have is that the temperature at x equals 0, right? The temperature at x equals 0, that is equal to TB. Or in other words, we have, let me write this in green. We have theta 0, that equals theta b, which is equivalent to TB. Perfect. Okay, so now that we have that, we can continue on to now solving the ODE. All right, so first step was to basically non-dimensionalize this ODE. Second step was to get all the boundary conditions. So now the third step is solving the ODE. Okay. And so some of you might notice that this equation is a second order constant coefficient differential equation. And so you can basically, if you don't have experience with differential equations, basically, when you see these kinds of equations, the first thing you want to do is assume that an exponential function works because it's the only one that will allow you to take two derivatives of the original equation and equal the original. And so what it ends up is that you basically get a general form of C1. So you have two constants, right, because of the two derivatives that you're taking that disappear. So you would have an e to the mx plus another one e to the minus mx. So you have as a combination of the two. And some of you also might notice now that we have an e to the minus. And so what we can do is now we can write this as a general solution in terms of hyperbolic cosine and sine. So cosh and sinh. So we have the general solution, which is going to be basically theta of psi is equal to C1 cosh ml psi plus C2 sinh ml psi. Perfect. Okay, so now that we have a general solution, I'm going to go back up to how we define theta. So we define theta as t of x minus t infinity times divided by tb minus t infinity. So we can write this theta general solution also as a temperature general solution. And so I'll put that right below. We get t of x is equivalent to theta psi times tb minus t infinity plus t infinity. Okay, perfect. And then just for future reference, if we were to take the derivative, I will give you the derivative right now. And I'll give it to you, sorry, I was using lambda. I'll give it to you as m tb minus t infinity times c1 sinh mx plus c2 cosh mx. So these are also some other important equations to keep in mind. Okay, so now that we have the general solution, what's our next step? Next step is to apply the boundary conditions. So let's go down here. Apply boundary conditions. So we'll first apply the fact that t at 0 equals tb. Okay. So if I was to, look at this general equation that I have for temperature, not the derivative, not theta, we can jump straight to the temperature. We see that if I plug in this, we get TB equals. I'll write out the full form of theta, so you can see TB equals C1 cosh ml psi plus C2 sinh ml psi. All of that, right? All of that times TB minus T infinity plus T infinity. Okay. All right. So now that we see this, we can basically um, start, you know, solving for whatever C1 and C2 can be. So this is when psi is actually 0, right? So we have the boundary condition is t at 0 equals TB, so x must equal 0. So this, remember, psi was x over L, so this becomes mx, and so this basically goes to 0, right? Same thing with this. Psi is x over L, L's cancel out, x times m, x is 0, so this also goes to 0. And so what we end up getting is that sinh of 0, remember, sinh of 0 is 0, and cosh of 0 is 1. So we have TB, right? If we say TB equals C1 times 1 plus 0, right, times TB minus T infinity. And I'm going to go ahead and subtract T, actually, let me do this so you can see it better. TB minus T infinity here. So all I did was basically just subtracted T infinity already from both sides. And so now you can see that we have a TB minus T infinity, a TB minus infinity. If I was to divide both sides by TB minus T infinity, what I end up getting is 1 equals C1. So C1 is essentially 1. So this is an important result. So I'll go ahead and box that. Perfect. So now what we can do is we need to apply our second boundary condition. So our second boundary condition was we're going to use the insulated tip. So what that means is our dt dx at x equals L, that equals 0. So you can see that I wrote the full form of the dt dx up here. I'm just going to go ahead and transplant that. So we have that 0 equals m times tb minus t infinity. We know that c1 is 0, and so what I can write this is as sinh ml plus c2 cosh ml. All of that basically equals 0. Okay, perfect. So then what I can do is I can divide both sides by m, all these constants, right? So these, you have to recognize that constant. So this basically comes down to 0 equals sinh ml plus c2 cosh ml, right? And what I can do now is that I can subtract sinh from both sides and then divide that by cosh. So if I was to do a subtraction on both sides, you would see now that we have this. And if I was to divide both sides by cosh, I get negative sinh ml over cosh. And you might recognize that a sinh over a cosh, similar to normal trigonometric functions, that equals a tanh. So that's a hyperbolic tan. And so C2 is essentially negative hyperbolic tan. So perfect. Okay. So now we can go ahead and write out our full equation. Looking back at the general form, we had, you know, the fact that T of x equals theta times TB minus T infinity plus T infinity. So now we know what the variables, what the constants are. So now let's write it as, we can write it, let's write it to the side, or yeah, let's write it at the bottom. So we have now T of x equals C1 equals 1, so then we have cosh mx, right? Cosh mx minus tanh ml times sinh mx, right? All of that in brackets times TB minus T infinity plus T infinity, right? So that's what we have. Perfect. So we have basically now solved for our temperature profile in the fin. We know how the temperature is decaying in the fin, and this is a pretty much all you'll need. But we can take it a step further and connect it back to heat transfer. So we can basically say that, go back to Fourier's law, Q of F, that equals, remember, negative K A dt dx, right? And so the heat flux at the wall would be at x equals 0. And now what you can do is you can calculate the heat flux now that you know the temperature profile. Take the derivative of this, you get dt dx, and now you can solve for Fourier's law. So you get the heat flux. And you can also do the same thing with efficiency. So you can calculate the efficiency of the fin by basically, so efficiency is usually denoted by that character. And so you put the heat flux divided by Newton's law of cooling. This is the B. And this A is basically the surface area of the fin. There's also a fin factor. So this is efficiency. There's also a fin factor. A fin factor is denoted by epsilon. So we have epsilon F, and that equals the heat flux, basically. Here, I should denote this as this is the surface area of the fin. This area, however, is the surface area of the base. So you can think of this as basically the width times 2b, and it has the same TB minus T infinity. So this is the fin factor, this is the fin efficiency, and this is the heat flux. So now that you know the temperature profile, you can do all of this. And this is for an insulated tip. You can do the same thing for other boundary conditions. It'll give you different answers, and the same thing can also be said for different geometries. You might see cylindrical fins, in which case the general solution will contain Bessel functions, and such. But this is a general process for how to do it. We first non-dimensionalize the ODE. We get whatever the boundary conditions are. We solve the ODE to get a general solution. We then apply the boundary conditions to solve for the constants. And then we basically then have the temperature profile. And then I'll catch you in the next one.